In the last few videos, I've talked about binding energy and mass defect. So let me just summarize these two ideas and look at a bit more about mass defects. Starting with binding energy. So specifically binding energy for the nucleus, for atomic nucleus. This is the work done, or we might say the mechanical energy needed. Okay, this is quite close to the wordings that you will find if you look up binding energy for the nucleus on Wikipedia, which is where I got most of the phrasings from. So mechanical energy needed to separate a nuclide into protons and neutrons. And if you remember what a nuclide is, it refers to a specific isotope of an atom. Mass defect. Again, for a nuclide. The mass defect, so this is the difference. The difference in mass, okay, between the nuclide and the sum of the separate protons and neutrons. So pretty much as I have described in the past 2 or 3 videos. Now with this understanding, I'm now going to take an overall view of the mass of the the binding energy of all of the elements in the world, or in the universe, if you like. So let's have a look. Maybe not all, just most of it. So what I want to do is this. I want to look at a graph. Now this is a graph of the binding energy per nucleon. Nucleon meaning either proton or neutron. Now it would be in units of MeV. Okay, so again, this is a graph that you can find using an internet search. Just search for binding energy per nucleon and plotted against the number of nucleons. Okay, so starting from 1 for hydrogen, put some marks here. So let that be 60, and so on until 240. And right, I'm going to take this to be 5, maybe 7 and 9. And just going to mark out a few values that are of interest in a moment. Okay. So binding energy per nucleon simply means that, say for each nucleus or each nuclide, you take the binding energy and divide by the number of nucleons. So let's take a look. Now for hydrogen, because it's just a proton, so there's nothing to separate, therefore the binding energy is 0. Okay, so that's simple enough. Now the next element from hydrogen is helium. So helium would have a binding energy per nucleon of close to 7. So let me put a circle there. That's for helium. G42. Now, and the next element is lithium. So lithium is around here, a bit more than 5. Okay, then it sort of goes up again to okay, there are a few more elements which I'll skip. I'm just going to go straight to carbon. So carbon is somewhere here, right? Let me write down lithium here. So that's lithium. Carbon is somewhere here, sort of less than 9. That's carbon 12. And then there is oxygen, which is probably somewhere here. Oxygen 16. And then somewhere along here would be iron, which is 56, and somewhere a lot further down, around here, let's say, would be uranium, 238. Okay. Now the graph, let's see what the graph looks like. Straight line up there. Just change to another color. Helium, lithium. Now there are a few elements between lithium and carbon, and a few more between carbon and oxygen. So something like that goes down, comes up, and maybe go down a bit, and many more elements to iron. Okay, and many more elements to uranium. Kind of a slighter curve downwards. So in between there are many elements which I've skipped, I've not shown. So I've just showed those that gives more obvious features. Right, so that's what an overall graph looks like for many of the elements that have that exist. Right. Now this graph is interesting. It's interesting for a very important reason. Now, let me perhaps start with uranium. Now, uranium, if you've learned about this previously, uranium was used to make the first atomic bomb. The actual isotope used for that bomb was uranium-235, but the binding energy is probably not too far from that. And in uranium-235, in that first atomic bomb, the uranium nucleus, the uranium nuclide was split into barium and krypton plus some neutrons. So barium and krypton have are lighter nuclides. So let's see. So they would be somewhere around here. Maybe somewhere around here and here. Okay, barium and krypton. But the important thing is that barium and krypton would have higher binding energies than uranium. So when uranium splits into these two, it would actually give out energy plus energy. Because krypton and barium has higher binding energy. Now if you remember that the binding energy has an opposite sign to the potential energy from what we have seen in the, I think, maybe 2 or 3 videos ago, you will understand that it means that energy has to be given out. Alright, this energy given out happens because the neutrons and protons in barium and krypton have lower potential energy and therefore higher binding energy, okay, than the neutrons and protons in uranium. So if a nuclide or nucleus somehow changes, in this case by breaking up into lighter nuclei, it is possible, therefore, from what we see in this graph, for energy to be given out. Okay, and that's how we can have so much energy in nuclear, what is called nuclear fission, which is used in the atomic bomb and in nuclear reactors. Now, in this case, at the opposite end of this graph, we have another example, another important example. Okay, what we have here is hydrogen. That's hydrogen here, and hydrogen, a lot of hydrogen is found in the sun. Right, in the sun. Now, in the sun, hydrogen nuclides, or just protons, are forced together very strongly by the gravitational forces, so strongly that they fuse together to give helium, to give the helium nuclide. Now from this graph you can see a big jump in the binding energy. Okay, a big jump in the binding energy, and this means that a lot of energy is given out, or a lot as in comparatively a lot compared to say uranium. Of course 1 or 4 hydrogen wouldn't give out too much energy when diffuse into helium. But when you have lots and lots, when we look at an example afterwards, as happens in the sun, a lot of energy will be given out, and that's how the sun gets its energy. It's by fusing hydrogen nucleus into hydrogen nuclides into helium nuclei. So this is the two important information that we would get from this graph. Okay, this what happens here is fusion. In the sun we have nuclear fusion, where hydrogen nuclei are fused together. So what you can see from this graph is that if an element moves towards the somehow either by fusing together or by splitting apart, move towards have products which are closer to the top of the graph, then energy can be given out.